Good morning, gang. Thank you guys for hanging around. I had to go run and take care of something real quick, but we are ready to get started. And I think you're going to enjoy today. This is actually a really fun lecture. So let's get QCam going. And we can begin. Okay. Oh, focus got there. Sometimes I swear this document camera has its own personality. So, last time you remember, we learned about integration by parts. Today we're going to do more integration by parts. Not convenient. So your homework 3 is up. I posted it Wednesday after class, and you should take your time with it. You know, it's not the hardest thing in the world. It really isn't. And the types of integration by parts problems that we've already discussed and we've already worked on, there's plenty of those in there for you to practice. But there is more to integration by parts than what we've seen. So today I'm going to show you some like startling and cool tricks. But I think before that, it would be worthwhile to get a little bit of practice with a homework problem or two. So I'll go ahead and remind you of the theorem. And while I'm writing this down for anybody who wasn't able to come on Wednesday, I'll ask you guys to type into chat just 1 or 2 homework problems that have been extra difficult or intimidating or something that you don't see how to do right away. So the theorem is really, IBP is how I abbreviate integration by parts, and it's a backwards product rule. If u is a function and v is a function, then the integral of u done dv is equal to u times v minus the integral of v done du. And then there's the version of it that is for definite integrals. It really is the same thing. You just have to remember to evaluate all the pieces. All right, so this is your backwards product rule. And going together with this, we had our LIPET rule, which tells us how to choose u. It's that hierarchy where if you start at the top of the list, you look to see if you have any L's, any logarithms. If you do, then you'll pick that to be u, and you'll pick everything else to be dv. If you don't have any logarithms, you move to the next thing on the list, which was inverse functions, I. If there are any inverse functions, then you'll pick those to be u and everything else to be dv, and so on. Okay, 10, 13, and 14 seem to be the problems of interest. Ooh, of course. While we're here, is anybody unable to get into WebAssign? Did anybody lose access? The trial did end. So if you're leaning on the trial version, you hadn't purchased an access code yet, I think you will have been kicked out. If that's the case, I can help you get back in. We can extend your trial access if you're still waiting for your access to code to come in the mail or something like that. But I need to know. You got to tell me so I can talk to our Cengage rep. They've actually been very helpful about that stuff this semester. I've been surprised. All right. So let's take a look at number 10. So we want to integrate w squared times the natural log of w dw. And it's a definite integral running from 1 to 2, so we're going to use this bottom formula. I have to pick parts of my integrand to call u and parts to call dv. If I think about my Lipet rule, L-I-P-E-T, remember this is log, inverse, polynomial, exponential, and trig. Remember the way this works, you run down this list, and the first time you see something that you actually have in your integral, you stop. And whatever that thing is, that's what you pick to be u, and then everything else will be dv. Now here, I stop right at the top, because I do have a logarithm. So I'm going to pick the logarithm to be u, and everything else to be dv. That's how that Lipet rule works. It's very convenient. So I'll fill out my IBP table. U is going to be the natural log of w. And that means dv has to be w squared times dw, everything else. And then we complete this table, meaning we need to calculate all the other pieces that are in this formula. So I've got u and dv, that means I need to get du and v. So du be the differential of ln w, that's 1 over w dw, and v will be the integral of dv, that's 1/3 w cubed. And that's my little IBP table. Just like with the substitutions, I like to put it in a box, get it out of my normal workflow. And because this is a definite integral, the version of the IBP formula I'm going to use is this one. So we'll tuck this off to the side too. Okay. So the integral from a to b of u times dv should be u times v. I'm going to write the polynomial piece out front because it just looks nicer. Evaluated between bounds, don't forget this. Oh, 1 to 2, sorry. Minus the integral from 1 to 2 of v du. So here's u times v minus the integral of v times du. We should evaluate this piece between these bounds. This is a 2, sorry, I just wrote a 3 there accidentally, but I've tried to make it clear that's a 2. And then we'll have to solve this integral still. But the nice thing is that since the integral involves du, not u itself, there's no logs here. So the logs are kind of what make this problem hard, and now they're gone. So this integral is definitely an improvement over the original. Okay, if I plug in 1 to this, I'll have 1/3 times 1 cubed times the natural log of 1. The natural log of 1 is 0. So I don't get anything here when I plug in my lower bound, but when I plug in my upper bound, I'll have 1/3 times 2 cubed, which is 8, times the natural log of 2. So that's 8/3 times the natural log of 2. And then minus, I'll pop this 1/3 out of the integral. And I have here integral 1 to 2. W cubed times 1 over W, that's W squared dW. So this is going to be 8/3 times the natural log of 2 minus 1/3 times integral of W squared is 1/3 W cubed. And this is evaluated from 1 to 2. And now this piece we need to evaluate. If I plug in 1, I'll get 1/3. If I plug in 2, I'll get 8/3. So I'll continue this on this next little page here. This is 8/3 times the natural log of 2 minus 1/3 times 8/3 minus 1/3. And 8/3 minus 1/3 is 7/3. So I guess if you really wanted to, you could write that as 8/3 ln 2 minus 7/9. And that's it. Of course, there's no plus c here because this is a definite integral. Our answer should just be a number. And nothing here is too hard, right? You just set up the IBP, trust your LIPET formula to help you pick u and dv, and then run the process. So this is a really good example, really middle of the road problem. This would be a perfectly fine exam problem, right? This is about exam caliber. Not too hard, not too easy.
Question.
Mm-hmm.
There's this long problem, problem 9, where we have to, so there's a lot, it didn't really follow thing because it tells us to put u, trig as a u. Is it because it didn't follow LIPET? Is it because it was like looping?
Yes, so this is when I mentioned that I'm going to show you some non-standard stuff, some integration by parts problems that are not super straightforward. Number 9 is one of those. So this is, yeah, the name for this sort of thing is called a looping integral, and I am going to show you how to do these today, but I wouldn't expect you to know how to do this just yet. So this guy, where you have an exponential times a trig function, specifically like an e-based exponential times sine or cosine, those I will show you how to handle today. They are certainly a special case, and they are tricky. So this one, I'd like to do one more kind of easy example, and then I'll show you how to do this one. Those are indeed tricky problems. Let's see. This, I think, is going to turn into a looping integral after the substitution. Let's take a quick look at 14, and then I'll come back to 9 and 13. 9 and 13 are both special problems. Whoa, shit. Oh, I hit view source, didn't I? All right. Oh. It's 14, yeah, e to the x, e to the minus x, and x equals 1 about the y-axis. This is homework 3, number 14. Oh, did I write homework 2 on that last one? Yeah, these are all coming from homework 3. Okay, here we go. Hold the space bar to talk, Griffin. Think of it like a walkie-talkie button. Okay, so this is actually a cylindrical shells problem. They ask you to do this by shells. But the integral that you get out, you can't do via the methods that we knew when we learned cylindrical shells. So that's why it lands in this section. So we're just kind of trying to remind you how to set up cylindrical shells problems. I'm going to graph these two functions, this curve, and then imagine revolving around the y-axis. So e to the x he looks like this. E to the negative x, like this. And x equals 1, we'll say is right here. So the region that's enclosed is definitely this region. And we want to revolve this around the y-axis. So this is my picture. The graphs of e to the x and e to the negative x, questions I get a lot like on exams, we're not allowed to use Desmos, what sort of graphs. These are definitely graphs you need to know, right? Just like the natural log graph, basic polynomial graphs, these are graphs that you should know. So coming up with this picture shouldn't be too hard. This point right here is of course 0, 1. This point over here is 1, e, and this point down here is 1, e to the negative 1. Since I'm using the cylindrical shells method, I should draw my strip in how? Is it going to be horizontal or vertical?
Vertical.
Right, remember it's always, for the shells method, it's always parallel to the axis of rotation. So here my axis of rotation is this vertical line, so my strip will be drawn in vertically, parallel to that line. So here's my little strip. That means its thickness is a dx thickness, so my integral will be a dx integral, which is convenient. I need to think about two stats. So if I revolve just this strip about this axis, and remember, has everybody looked at those visualization videos I posted in Canvas? If you haven't, please do. It'll make this stuff make so much more sense, I promise. So come down here, here, the cylindrical shells visualization video. This is very good. If you haven't done this, go ahead and pop open a tab and leave this link open. You don't have to watch it right now, but pop this in a separate tab and take a look at him down the line. Because if I imagine revolving just this strip, I'm going to get a little cylindrical shell. I'll do my best to draw it to proportion here. Although surely I am no artist. You get something looking about like this. And it has a height. The height of the shell comes from the height of the strip. And it has a radius. And the radius of the shell is the distance from the strip to the axis of rotation. So it's up to us to find R and H. And to do that, usually we talk about characterizing these points that are on the curve at the strip here. So this point right here would be x, e to the negative x. And this point right up here would be x comma e to the x. Because they're like generic points on the graph of e to the negative x and e to the x respectively. So what is this horizontal distance r? The horizontal distance from the axis of rotation to my strip that becomes the radius of my shell. Yeah, good. This is just going to be x, right? Because the x coordinate at this point and at any point along the strip there is x. So that horizontal distance coming from that x coordinate, r is x. What about the height?
E to the x minus e to the negative x.
Very good. Yeah, it's the difference of y values, right? You take the y value here and you subtract the y value here. The y value here is e to the x. The y value here is e to the negative x. So the height is e to the x minus e to the negative x. And then remember the formula for dv. You can imagine coming in with sharp big scissors, cutting and unrolling the shell. So your dv is the height times the thickness times the circumference of that circle. That's 2 pi r times h times dx in this case, because the thickness of my strip is an x thickness. So here, that is 2 pi times x times e to the x minus e to the negative x dx. So we're going to have to integrate this in order to get our volume. We're going to integrate from whatever the x value is all the way over here to whatever the x value is all the way over here. That's 0 to 1. So v is the integral from 0 to 1 of dv, which is the integral from 0 to 1 of 2 pi x e to the x minus e to the negative x dx. And we can pop the 2 pi out and then actually get to work on the integral. And this guy, although he may not look like it, is an integration by parts problem. He does look like it. We saw that x times e to the x integral on Wednesday. If you distribute this x, then you'll have x times e to the x minus x times e to the negative x. So each one of those is very similar to the examples we looked at last time. And that might be the most natural way for you guys to think of this right now, although it's certainly not the only way. You could think of it like this. All right, I'm distributing this x over these parens. And then I make sure that the 2 pi still goes to everybody. So I'm putting these big parentheses out here. And then each one of those is a little integration by parts problem. You could do this by parts, and you could do this by parts on their own, separate from one another. It's not the only way to do this, mind you. You could do this thing by parts as a single guy. If I follow my Lipet rule, I don't have any logs, I don't have any inverse functions, but I do have a polynomial. The x here is a polynomial function. So I'd use this as u and this as dv. But if I remember what it's like being in Calc 2 well enough, then I think probably most people would want to do this. Probably most people would split it up. Because each of these problems looks familiar.
Would take longer.
It would, yeah. I think doing it directly from here would be faster, and I'm tempted to do that because I see it can be done. But I just want to point out that this would be just fine, you know, and I don't have a problem doing this. I think this is probably what most people would do. So even though we could attack direct from here, I think the more natural thing to do for a typical Calc 2 student would be this, but either one is totally fine. I'll run through it like this since we've already started here. But then we can come back and make a little comment on how we would proceed if we wanted to go from there. Let's see. So each of these are going to get their own IVP table. Here, I'm going to let u be x and dv be e to the x dx. And over here, I'm going to let u be x and dv will be e to the minus x dx. If u is x, then du is just dx, and v here, if dv is e to the x, then v is e to the x. So that's my first IVP table. And my other IVP table here, again, if u is x, then du is dx. And here, the integral of e to the negative x is negative e to the negative x. So this is my other IVP table. If I replace each of those integrals by their IVP equivalents, just using that formula, this is going to be u times v, so evaluated between 0 and 1, minus the integral from 0 to 1 of v du. And then minus 2 pi times, now I replace this guy by his IVP equivalent, which is negative x e to the x, negative x e to the negative x, sorry. Evaluated from 0 to 1 minus the integral 0 to 1 of negative e to the negative x dx, like so. Did you guys see the cat walk by in the background? Was it a white cat or a black cat? No, are you stealing your brother's food? Oh, oh. Sorry. One of my cats is very greedy. Okay, so if I evaluate this piece between 0 and 1, I plug in 1, I'll get 1 times e. And then I subtract what I get when I plug in 0. That's going to be 0 times e to the 0, or 0 times 1. That's 0. So that first piece is just e. And now this guy, when I integrate him, the integral of e to the x is e to the x. And I evaluate that between 0 and 1. Something similar happens when I do the evaluation here. If I plug in 1, I'll get negative e to the negative 1. If I plug in 0, I'll get negative 0 e to the 0. And again, so that 0 guy contributes nothing, only get something when I plug in 1. So negative 1 e to the negative 1, or I'll write it like that for now, why not? And then minus. Here I've got 2 minuses, that'll make a plus. But then when I integrate, I'll get a third minus. So it really is going to be minus e to the negative x here from 0 to 1. And this game with minus signs piling up, having lots of minuses and lots of parentheses, is pretty typical of an integration by parts problem.
Do we have this problem?
I'm sorry?
Do we have to change bounds for this problem because it's indefinite?
No, because I'm not making any substitutions.
Okay.
Yeah. So this e to the minus x integral, you could do that as a substitution. And if you must, then you can. And if you're going to do the substitution, you should write it out and change the bounds. But here, I know the integral of e to the negative x is negative e to the negative x. So I'm thinking of it like those 2 minuses come together, and then I get a minus from the integral. And I know how to do that integral without making the substitution. So I'm just going to go ahead and do it. It's a micro u sub. The result will be the same either way. So here this is e, and here when I evaluate between bounds, at the upper bound I'll have e, at the lower bound I'll have e to the 0, which is 1. So this is e minus 1. And then this piece will be minus 2 pi, negative e to the negative 1. And then this minus I could pop out, or I'll do it as it's written here, plus. So when I plug in 1, I'll have negative e to the negative 1. And then when I plug in 0, I'll subtract what I get when I plug in 0. That'll be minus, and then negative e to the negative 0. That's minus 1. So lots of parentheses piling up, lots of negatives to distribute carefully. But as long as you are patient and careful, everything will go just fine. This is 2 pi, e minus e, that's 0, and then minus negative 1, that's 1. So this piece right here is just 1 minus 2 pi times. Here I've got negative e to the negative 1 plus negative e to the negative 1, that's negative 2 e to the negative 1. And then no negative to distribute here, so this is just going to be a plus 1. So altogether, I've got 2 pi, come on, pen. Altogether, I've got 2 pi, that's this guy, plus 4 pi e to the negative 1, distributing the negative there, and then minus 2 pi. So these eat each other up, and you get 4 pi over e. Because e to the negative 1 is 1 over e. Okay. So I agree with the observation that this takes a little bit longer, right? Where you do both of the integrals separately. What we see in the end is that there's a fair amount of cancellation, and that if we were brave, we could have handled this all at once with a single IBP. But way more important than being efficient is being correct, right? So there's 3 rules of good mathematical writing. Be correct, be clear, be brief. And in that order, make sure you're correct first. That's what matters the most. Don't write down something which is not true. And then make sure that it's clear. Make sure that your reader can tell what the fuck you did. And then and only then do you worry about brevity, about being short, right? So this is not the shortest solution, but it is a correct solution, and it is a clear solution. So that's fine. We don't need to stress about brevity. If, however, you are concerned about being sufficiently brief, about the length or the amount of paper that this takes, you could come back here. And at this step, you could run your IBP as follows. U equals x, dv equals e to the x minus e to the minus x dx. But then you'll have to be able to integrate this quickly, right? The dv to v step here is a little bit rougher. Du is just dx. But v here would be the integral of e to the x minus e to the minus x dx. That's e to the x plus e to the minus x. And this is the alternate attack. So you could take care of it all in one thing if you're sufficiently comfy with the micro u sub there. And then you would have this times this evaluated from 0 to 1 minus this times this in your integral. And the integral of this is where most of the stuff is going to come from. But you don't have to. The way we did it here is just fine. And like I said, I think that's the way most of my students in the past would approach this problem. There's nothing wrong with that. Questions on this guy? Okay, then I have a totally unrelated question for you. Does anybody know what a dash pot is? Okay. Yeah, it's a weird term, and unless you've worked construction, you probably wouldn't have heard it. Everybody's been into and out of a convenience store, though. And everybody knows what happens if you try to slam the door at a convenience store or any other big retail institution. You can't. You try to slam the door, and there's this little hydraulic thing at the top that goes, and it won't let you. It's a little oil-filled cylinder that has a piston moving back and forth in it that dampens the motion of the door. So the door doesn't move too quickly, it doesn't accelerate too quickly. That thing that goes and doesn't let you slam the door, that little hydraulic thing that you see at the top with the folding arm, that's called a dash pot. Dash pots are common dampeners. What they do is they limit acceleration. So they smooth out motion. And they also have the effect of dampening motion over time. Imagine the following situation. I've got a little cart on wheels here, and on that cart I place an object of a certain mass. Over here I have a wall, and attached to that wall I have a spring. And I connect the spring to the mass. If I pull this sumbitch back and I let him go, then he's going to start bouncing back and forth. You imagine that this is a friction-free environment. Maybe this is magnetic levitation or whatever. It's just an ideal world of physics problem. He bounces back and forth as what's called a harmonic oscillator. If on the other side I attach a dash pot, then you get what's called a damped harmonic oscillator. It will still go back and forth, but it's going to go back and forth less and less and less each time, and then it's going to stop. Or, you know, in the ideal world of physics, it would never stop. It would just go back and forth less and less and less. This is what's called a damped harmonic oscillator. I always forget whether oscillator has one L or two. I think it might be two. You're going to see this physical system again when you take differential equations. MAP2312, this is a famous physical system. The way I've drawn it here with the mass on wheels and the spring and the dash pot is a highly simplified version, but versions of this appear all over the place in nature. If you're looking at an orbit that's not stable, where the planet or whatever, the satellite is going to come in and crash into whatever it is that it's orbiting. If you look at that straight from the side, that will look like a damped harmonic oscillator. Because as it goes around, looking from above, if you just look on the side, it just looks like it's going side to side. And then of course the dampening as the orbit comes in closer and closer. So this sort of physical system is really important. And it's one of the things that you'll study in the first few weeks of MAP2302 when you talk about linear, constant coefficient, ordinary differential equations. The solution to this, the equations of motion that you get out when you solve that differential equation look like this. So if S is the position, if this is the S axis, and you're thinking of this thing as bouncing back and forth here over some amount of time, then the position of that cart after you release it will follow something like this. Cos t, we know what that looks like. That's a regular cosine wave. Slapping this e to the negative t on there is going to dampen the cosine wave down to 0. I'll show you in Desmos. Oh, sorry, this is something I was working on for my Calc 1 class. I'm going to exaggerate here the dampening. We just look to the right. You see here you start off with a regular cosine wave, but it's getting smaller and smaller and smaller. That's the dampening effect. The e to the negative t is like squishing the cosine wave down. So it'll continue to oscillate, but those oscillations will get smaller and smaller and smaller over time. This is the damped harmonic oscillator. And what we want to do is integrate. And in physics, you could be finding like the total distance traveled or the amount of work done or anything like that. You would need to integrate an object like this. So how do we, that's enough motivation. I don't really care about the differential equations. This is not a differential equations class. It's also not a physics class, but I do care about the mathematics that you're going to want to do to this sort of thing. So how do we evaluate integrals of stuff like this? And it could be e to the 2t cos 5t, or e to the negative 10t cos 12t, or e to the negative 0.1t cos 3t, any of those. How do we evaluate stuff like this? The answer is, these are called looping integrals. So first, by parts, using the technique we just learned. And this is called a looping integral. And I'll show you, you'll see why it's called a looping integral in just a second. I do have videos up in Canvas of Patrick JMT and a few other people, I think, solving looping integrals and discussing looping integrals. This tends to be a tricky thing, and what I'm about to show you may look a little bit like magic. It may melt your brain a little bit. But just try to follow along as best you can. And then if it still feels like magic after we're done explaining, after class is over, go through and watch a few more examples from, from that modules page. All right, let's just try it. I'm going to run IBP, and your LIPET rule really isn't very useful here because you've got exponential and trig. Those are the two bottom things. And it turns out it really doesn't matter which way you go. I could pick this to be u and this to be dv. Or I could pick this to be u and this to be dv. We're going to run integration by parts twice. And as long as you're consistent, you either have to choose the exponential to be u and the trig to be dv in both instances, or the other way around. So I don't really care. Let's do it like this. Let's follow our LIPET rule. So I'll let u be the exponential and dv be the trig, because exponential is above trig on our LIPET rule. And then du, the differential here is negative e to the negative t dt. And v, the integral of cosine, is sine. So here's my first IBP table. I'm going to need a second eventually. So this tells me that the integral of e to the negative t cos t is equal to u times v, that's e to the negative t times sine t, minus the integral of v du. That's minus e to the negative t sine t dt. I can pop this negative out. So I get e to the negative t sine t plus the integral of e to the negative t sine t dt. And what you recognize is that the integral you have here is very similar to the integral we started with. And if the way to do this is by parts, then the way to do this has to be by parts. So we're going to set up another IBP table. Again, I'll pick u to be the exponential and dv to be sine t dt, everything else. So that du is, again, negative e to the negative t dt. And here v is going to be negative cos t, the integral of sine t. And then I come back over here. The e to the negative t sine t out front comes along for the ride. And now to that I need to add this guy's IBP equivalent, which is e to the negative t times negative cos t, that's u times v, minus the integral of v times du. And they've got two negatives here, right? Negative e to the negative t times negative cos t. So I'm just going to write that as e to the negative t cos t dt. And then you stare at this for a minute. The integral I want is equal to this stuff minus the integral that I want. Let me arrange this in one line. What I have here is the integral of e to the negative t cos t dt equals e to the negative t sine t. This is going to be minus e to the negative t cos t minus the integral of e to the negative t cos t dt. Is everybody following me so far? Take a second and make sure you're comfy up to here.
Can you hear me?
Yeah, what's up, Griffin?
Hey, could you explain again why you did IBP a second time?
Well, the integral that I got out after my first run of IBP was this. Right? I did IBP once, simplified a little bit, and the integral that was left over is again like e to the negative t times sine or cosine. It looks very, very similar to the integral I started with. So whatever I was going to do to integrate this, I should probably do the same thing to integrate this. It's just intuition. Think of it as coming from foresight, right? Are we comfortable with the mechanics that get us to this line? Because this line, once you're here, it's all done. You might not see it yet, but the entire answer is about to fall out without doing any more work, without explicitly solving the integral ever. If I called this thing, if I gave this thing a name, Sam, then Sam is equal to this shit minus Sam. Or if I called this thing X, then X is equal to this shit minus X. We all know how to solve that equation for X. You add this thing over and then divide by 2. So I'm going to add this integral to both sides. What I have over here is e to the negative t cos t, the integral of e to the negative t cos t. And over here, I have minus integral e to the negative t cos t. So when I add this to both sides, I'm going to get 2 copies of the integral of e to the negative t cos t dt equals this stuff. And then, holy shit, I can solve for this integral just dividing by 2. And we should tack on our plus c. But that's it, ladies and gentlemen. These are called looping integrals because after some procedure, you get your integral is equal to some stuff minus your integral. Your integral, the original problem, showed back up again. So rather than trying to evaluate this integral directly, you add it back over and then solve algebraically. It's very, very clever. So I'll give you a second to get things written down, and then I'd like to hear any questions or thoughts you have. Think of it as coming in a few steps. There's everything that gets you to this line, and then there's understanding that this line tells you how to solve the problem. You don't evaluate either integral directly. You solve this whole equation for the integral, treating the integral like a variable. Usually when I teach this in class, I can see people's brains slowly dripping out their ear at this point. So I'm going to be patient here, and I want to hear what you guys are thinking. Yeah, I like it too. It's very cool. So what we did to solve this integral is run integration by parts twice. I run IBP once, and I get this. I simplify here. All right, just minus minus makes plus. So I run integration by parts once on my integral, and that gives me this. I recognize that this is very similar to the original problem. So I run integration by parts one more time on this piece. That gets me here. Now at this line, what I have is my integral is equal to e to the negative t sine t plus e to the negative t times negative cos t minus my integral. This and this are the same. So if I add this over here, I'll have 2 of these equals just this stuff. In order to make that easier to see, I like to write it in a single line. My original here, this is equal to this, right? So my integral, the problem I started with, is equal to this. The blue box stuff here is just this stuff. And what I recognize is that in this line, if I treat this object like a variable, then call it I, then I is equal to this shit minus I. And you can solve that equation for I by adding this over here. Since this integral and this integral are the same, when I add this to both sides, I just get 2 copies of this integral. I plus I is 2I. So I get 2 copies of this integral equals the other stuff that was left over. So how do we solve that? Just divide by 2. And then also you tack on a plus c because it's an indefinite integral. It's very, very sneaky. Essentially what you do is you set up an equation, you run integration by parts some number of times and do whatever you must in order to get an equation that looks like your integral equals some stuff minus your integral. Then you add I to both sides. So this implies that 2I is equal to that stuff, which implies that I is equal to that stuff over 2. It is a little bit trickier with a definite integral, yes, but not much trickier. Really, the way to handle definite integrals like these, each of these pieces here, you would evaluate between bounds, and then you'd have like my integral from a to b equals whatever you get when you evaluate this minus my integral from a to b, and then you add it back over. Really the same thing. There's just a little bit more to write and a little bit more to do with the definite integral because you have to evaluate, but it's not any harder conceptually. It's just a little bit more writing. Margaret asked a good question there. Can you go all the way through this process and then evaluate at the end? I want to say no, because one of the things I really want you guys doing when you do integrals by parts, definite integrals by parts, is to evaluate whatever pops out, the u times v piece, right away. But you could wait until the end to evaluate. It's going to mean more writing, because then you have to do all this stuff, and then you get to this end, and then evaluate. So I think you'll find that the way I've been suggesting you do it is going to be the fastest and cleanest way. But you certainly can. Yeah, it would be okay if this was the integral from 0 to 1 of this function. You could get to this step here, and then instead of writing the plus c, just evaluate this between 0 and 1. But you could have done that evaluation all the way back here. And then instead of rewriting this shit over and over again, you would just write the number that comes out when you do the evaluation. So either way there would be fine, Margaret. How are we feeling about this? Getting to this line and then adding over? It's usually a little bit shocking. I know I was shocked the first time I saw this. Okay, cool. So that's integration by parts. We're done. We're done with 7.1. Congratulations. That's all the sneaky shit I needed to show you today. But I do want to introduce what we're going to be doing next week, which is trig integrals. And there is a special trig integral that is a looping integral. There's actually a family of trig integrals that are looping integrals. So yeah, I know. First off, if you're not really sharp with trig identities, spend some time this weekend reminding yourself how trig identities work. So next week, all about trig integrals. It's section 7.3. There is a famous trig integral. A famous looping trig integral. So most of the trig integrals we're going to do will be done with some combination of u sub and trig identities. But odd powers of secant turn out to be a little bit harder to integrate. So the classic example is secant cubed. Also, secant cubed times tangent squared. Secant to the 5 times tangent to the 4. Any odd power of secant times an even power of tangent turns out to be tricky. So for all these trig integrals, you really want to study up your trig identities. Specifically, the 3 Pythagorean identities, sine squared plus cos squared equals 1, tan squared plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. Those 3 Pythagorean identities and half angle identities. Cos squared is 1/2 times 1 plus cos 2 theta. Sine squared is 1/2 1 minus cos 2 theta. And the double angle identities, sine 2 theta equals 2 sine theta cos theta. Those trig identities you need to have like right there on the top of your brain. And those will handle most of what we're going to do in section 7.3, but this guy's special. And anytime you see an odd power of secant times an even power of tangent, that is also special in the same way. So I want to show you how to do this. This is also a looping integral. the trick to doing secant cubed, integrating secant cubed, is to think of it as secant times secant squared. And to run integration by parts. So here I will choose u to be secant. This one really does live outside of the Lipet rule. There's no way to make Lipet work for you here because it's all trig. And dv I'll make secant squared x dx. Du, the derivative of secant, is secant tangent. And v, the integral of secant squared, that's just tangent. So I'll tell you now, one of the problems that shows up on pretty much all of my first exams is a problem where you get a choice to evaluate one of a few looping integrals. One of them will usually be a straight odd power of secant, and the other one will usually be a damped harmonic oscillator. So you need to practice the looping integrals. They will show up on a test. Here's u times dv. So the integral of u dv should be equal to u times v, which is secant x times tangent x, minus the integral of v du, which is tangent x times secant tangent. Okay, so that's going to be tangent squared times secant x dx. And at this stage, we use a trig identity. Tan squared x is secant squared x minus 1. This follows from sine squared plus cos squared equals 1. You just divide both sides by cos squared and you get tan squared plus 1 equals secant squared, and then you subtract the 1 over. So then, instead of running integration by parts a second time, you only need one run of IBP here, but then you use this trig identity. I replace tan squared by secant squared minus 1. And maybe you can see from this stage why this problem is going to loop. If I distribute this secant x across this term, one of the terms will be secant cubed. So I'll have integral of secant cubed equals some bullshit minus the integral of secant cubed. Let's see exactly what we get. This is secant x, tangent x, and then I'll distribute this secant. So I'll have minus integral secant cubed and then we'll also have the minus secant here. And then we're going to split that integral up. So this will be secant x times tangent x minus the integral of secant cubed x dx. And then these two minuses here will make plus the integral of secant x dx. So here's what I have. The integral of secant cubed equals secant tangent minus the integral of secant cubed. So I'm going to add this piece back over to make it loop, plus the integral of secant. Does anybody remember the integral of secant? We talked about this when we talked about u sub. This is a strange u sub problem on its own. The integral of secant is the natural log of secant plus tangent. And if you don't remember how to get this guy, I'll remind you next Monday. It's not terribly hard. It's a sneaky little trick and a U sub, but most people memorize this. So what we have is the integral of secant cubed is equal to some stuff minus the integral of secant cubed. I'll write it in a single line. And I'll put the two pieces here next to each other. So I'll have secant x tangent x plus the natural log of secant x plus tangent x minus the integral of secant cubed x dx. And this is what we mean by looping, right? My original integral is equal to some stuff minus my original integral. So now I add this back over. And I'll get 2 times the integral of secant cubed is equal to secant x tangent x plus the natural log of secant x plus tangent x. Then divide by 2. So the integral of secant cubed is equal to all this over 2. I'll write it as 1/2 times. And then at the end here, we tack on our plus c because indefinite integral. So yeah, this is the move. Some of these steps you could omit, of course. Here to here you need, but then from here you could probably jump straight to here if you're observant enough, and then from here you could jump straight to here, and then from here you could jump straight to here. But this is the procedure. So the odd powers of secant, they're tricky integrals. They require integration by parts, and they loop in the same way that the damped harmonic oscillator loops. This, I think, is about where we're going to leave it. Yeah, and we're just out of time right now. So this is where we're going to leave it for today. The vast majority of your homework this week is just straightforward IBP problems. There are a few looping problems in there, maybe just the one looping integral in number 9. Yeah, I don't think I gave you any others. Oh wait, this guy, after you make the substitution, he'll loop also. So a quick comment on number 13. You need a trig identity here. Sine of 2t is 2 times the sine of t times the cos of t. So to make number 13 go, I would write this down. For number 13, you need the identity. I'll write it right here because we've already got the word identity. Sine of 2t is 2 times the sine of t times the cos of t. You need this on 13. And then you make the substitution, x equals cos t, and this will become a damped harmonic oscillator. So 13 and 9 are both looping. Do 9 first. 9 will walk you gently through the procedure. I know that the WebAssign stuff, when it makes you go through the process slowly, can be a little bit frustrating. But try to be very patient with it. Maybe consider rewatching this video or look at some of the things that I've posted on Canvas, where Patrick JMT solves a few looping integrals. And then be patient with WebAssign on number 9. And then when you come down here to number 13, remember it's really the same thing. You just have to make a substitution first. In order to make that substitution go, though, you will need this trig identity. All right, that's where I have to end it for today, guys. Yeah, I hope everybody has a nice, wonderful, safe weekend. I do have, let's see, actually, do I have an office hour? I think I have an office hour this afternoon. Friday office hour, 2 to 3 p.m. Yeah, so I do have an office hour this afternoon if you want to come by for some help solving problems. Of course, I will be there. Otherwise, you can always send me a message on Canvas or anything like that. But yeah, work hard on getting this homework done. Next week, we're going to talk about section 7.3 and 7.2 and 7.3, sorry. Trig integrals is section 7.2. And then 7.3 we will also talk about next week is trigonometric substitutions. So that's where we're going. You want to stay on top of the homework because the next week or two's worth of homework is tough. There's a lot of it. And as you go through all these integrals and you learn all these methods to solve integrals, make sure you're writing things neatly, make sure you're doing them by yourself, make sure you're training yourself. All right? It might sound derogatory, but it's not. We all need to train ourselves to do the things we want to do. So right now you're training. Make sure that you're training well. Use good form, right? Just like at the gym. Don't practice bad. Practice correctly, and everything will go nice and smooth. If you have any questions, don't hesitate to reach out. Again, Canvas and office hours are the best ways to get a hold of me. And I'll do my best to be very responsive for you there. So yep, have a great weekend. If you have questions, please ask. And otherwise, I will see you guys on Monday.